questions, right? In the morning class, we had taken the scaling laws in miniaturization. In that one, I had already told we'll be discussing these outline of the chapters. And I think that in the morning session, we had taken up to the trimmer's force scaling vector. In that one, still we are supposed to calculate power by volume ratio. That power density you are supposed to calculate. We'll try to see that. And whenever you go for the miniaturization, you had to remember two types of scaling laws here. One is when you design this microsystems, one is with respect to the size of the physical objects, and second one is with respect to the behavior of the microsystems. So these two we have to consider whenever you go for the scaling laws, when you apply it for the design of microsystems. And later we discussed here, when you go for the scaling in geometry with respect to the physical quantities here, we'll be having two parameters. One is volume and second one is the surface itself here. Whenever you go for the micro design itself here, these two parameters you have to keep it in mind, where volume will relate to the mass and weight of the components here, and other when you relate it to the mass and weight, the volume here, we'll be having one more parameter which you have to consider, that is nothing but the mechanical and thermal inertia. And later we had taken, whenever you go for this thermal inertia here, it will be related to what? It will be related to the heat capacity of the solid here, where you can measure how fast or the solid will be able to heat or cool itself here. And later we discussed about a few more parameters here, like by taking one example, and all the examples will be considering by measuring in the form of linear dimension, that is L here. So we'll be taking surface to volume parameter here. So that S by L ratios will be considering. So where we'll be having surface to volume ratios will be, if we take it for two different objects, then that value will be differing here because of the amount of food it is being consuming, amount of energy and power that is being consuming will differ the values in the S by V ratio. And that one we had taken in the previous class itself here in the morning session. And later we discussed about when you take it in the rigid body dynamics, how the miniaturization will be taking place here. So in that one, in dynamic forces, we had taken a few parameters like the velocity, force and acceleration. These 3 points we had taken, and how the m will be represented in the form of L cube, f will be represented in the form of L to the power of 4 into 10 to the power of minus 2 into 10 to the power of minus 2, and acceleration and velocity can be represented as what? L into t to the power of minus 1. So we had taken this one in the previous session. And later we discussed here, we are taking the trimmer force scaling vector, where the force scaling vector is represented by F is equal to what? L to the power of F, which is given by L1 in the matrix form of from L1 to L4 itself here. For that one, we have calculated the acceleration, which is equal to this value, right? L to the power of minus 2, minus 1, L0 and L1 here. And later what we have taken, we had also calculated the transit time for that one here. So which is given by L to the power of 1.5, L to the power of 1, L to the power of 0.5 and L to the power of 0. So till here we had taken in the morning session here up to the transit time. Transit time, that is with respect to the trimmer force scaling vector, we had taken itself here. Now let us go for the next parameter here, that is nothing but power density, right? Let us take down here power density. You can just have a glance on this one. We'll start discussing. So if you take it here, the power density, you can see it in the slides, all of them, right? So power is a major parameter, right? So whenever you go for designing the microsystems here, the power plays a vital role here. So if there is no sufficient power supply to the design here, microsystem design here, then automatically what happens? It leads to what? It leads to the inactivity of the system, or it will also suffer structural damage here. What structural damage it will be suffering, such as the overheating with the excessive power supply. So if you have excessive power supply, then overheating will be there. If you have insufficient power supply, it will not be working. There will be no activity for that one here. So the power plays a very important role in microsystems here. So how much power, right? How much power is supposed to give it for the microsystems? And if you give less power, it leads to inactivity. If you give excess power, it leads to the structural damage and overheating here. So these parameters you have to consider. For that one, we are discussing about the power density here. So here, if there are some excessive power requirements for the microsystems, what happens? It leads to the increase in the operational cost also. So more power requirements, if the microsystem design requires more power here, excessive power is required means, then what happens? Then the battery, right? The battery operational cost will be a drawback for these systems here. And also what happens, it also will reduce the operational lives of the biomedical systems here. Suppose if the biomedical devices have been implanted to the human body here, their lives, right, the operation lives will be reduced itself. You can use it for only certain period of time. After that certain period of time, once again you have to replace. Then it would be really, right, it will be really costlier, and you cannot use the such devices in the biomedical devices in the human bodies itself here, right? So for that one, what we had to do, we had to deal with this one, right? We had to deal with what? We had to deal with the power density than the power supply per second here. So for that one, we'll try to take one after the other here. So when you want to deal with the power density than the power supply per second here, we'll define now. We'll define one parameter known as a power supply here, P per unit volume. So power density is defined as what? Power supply per unit volume. So P by V naught is nothing but the power density. So let us obtain that equation for that one here. So how do you obtain this equation here? So first what we'll do is we'll try to take the derivation for the power supply. I think who is that one? You can mute yourself. So here, when you want to derive the power supply with the work that is required for the mass and distance here, so let us find out the equation for that one here. So what is the equation for that one? The work done, right? The work done is equal to what? It is equal to force into the distance traveled. So the power is defined what? The power is defined as what? Work done per unit time. So P is equal to W by T. So what would be the power density here? The power density is nothing but P by V naught here. So P by V naught, if we take it here, what we'll get? We'll get Fs by T into V naught itself here. So this will be the expression for the power density, right? So this will be the expression here. So P by V naught, if we take it the value, right, which is nothing but Fs into work done, right? Work done is nothing but what? F into S divided by V naught. V naught is nothing but the volume. So volume is given by T into V naught itself here. So this will be considered for the equation for the power density here. So this is the power density equation here. So which is taken as what? Work done per unit time here. So W by T. So W is given as F into S. So W is nothing but F into S here divided by T, right? And V naught we are taking as it is as V naught itself here. Now let us substitute in the form of linear in the form of the linear scale parameter here. So F by V naught will be equal to what? Fs is given by F is nothing but L to the power of F. S surface area is nothing but L to the power of 1. Distance, sorry, distance is L to the power of 1. Surface area will be L square, right? And T, right? T will be here V naught. V naught, how do you represent this V naught here? So V naught is nothing but L to the power of 1, right? L to the power of 1, L cube, L to the power of minus F, and L cube itself here. So this will be the value for V naught. So what is V naught here? It is nothing but the volume here. Power supply per unit volume. So if you see the previous slides, I think they will be able to get the value for volume. Yeah, initial velocity it is. So volume is nothing but what here? This is the volume value is nothing but L cube. Just a second. Where I calculated the volume. Yeah. So here it is, right? So volume is given by A into B into C, which is nothing but L cube itself here. So that L cube will be considered. Yeah. So here it is, right? So uh, T into V naught is represented by this value here, right? So L to the power of 1, L cube, L to the power of minus F into L cube here. Substitute, then we'll be getting L to the power of 1.5 F, right? 1 minus this value, right? Then L to the power of minus 4 here. So this equation can be once again written as L to the power of F into 1 to the power of 5 into L to the power of minus 4 here. So substitute, right? So if you substitute, then you'll be getting this value L to the power of 2 to the power of minus 2.5, right? Minus 2.5, L to the power of minus 1, L to the power of 0.5, and L square here. So this will give you, right? This will give you the value for what is this one? Power density. So here this L cube is nothing but volume, where you can see it here, right? T into V naught. V naught L cube is the volume. This value L to the power of 1 L cube L to the power of minus F, it is nothing but transient times here. So this one is nothing but the transient time here. So this transient time T is been substituted here. So this is the transient time here, right? So this is the transient time, right? So this transient time is been substituted. So then we'll be able to get this answer here. L to the power of 1.5 F, right? So instead of substituting here L to the power of F, we are kept as it is, right? So L to the power of F is kept as it is here. I think, yeah, this one is kept as it is. I think we'll get this value, right? L to the power of half into LF. So this value is been taken here, right? L to the power of 1 into L cube into L to the power of minus F. So this will be the transient time here. So this, but here the value here taken here is for the unit time. So that value is been substituted here. So later we'll get this equation here. So this is the value, right? This is the value for power density. L to the power of minus 2.5, L to the power of minus 1, L to the power of 0.5, and L square here. So this equation will consider for rigid body dynamics here. So here it is, right? Here it is when you go for the order levels here. So ordered level 1, 2, 3, 4. So this will be the force F value, right? This will be the acceleration value, and this will be the time value, and this will be the power density value. So if you take for order 1, right, these are the parameter values, and if you take it for order 2, these are the values here. So this value in terms of linear scale you can calculate. So these are the scaling laws, right? These are the scaling laws here, and for the rigid body dynamics you can see it in this table here. So here this will be used for design process, right? So you will be using for a design process here. So here if you see this order number, right, if you see this order number here, it is nothing but order of reduction that takes place in the force scaling vector here. So the second, if you take it here, right, if you see in this figure, you can get this one, right? You can get this order number, and how for this order, right, how we'll be able to get the force scaling vector. So that is the scaling laws for the rigid body itself, right? So this is about the scaling laws. I hope you have understood. We'll go for the next heading, that is electrostatic forces here. Shall we go for next slide?
Yes, ma'am.
Okay. A little, this one is there, right? Here, just a second. So if you see this equation, this T equation is wrong little here, right? This T equation is little wrong, right? So here I had to represent L cube. Just a second here. Okay, this equation is actually wrong, right? So here I have to get to the power of half, because if I see the equation, time equation, so here I have to write 1 by 2, 1 divided by 2, because if I see this one, right, if I take the transient equation, I'll just show it here for you all, right? So you're not getting the correct answer. If I see this transient equations, right? So this one it is, right? So L to the power of 1, right? L cube, L to the power of minus F to the power of minus 2 it is, right? So I had to take this equation only for transient time. So I have not taken that equation. Let me copy it. So this equation I had to apply it for here. I think now it is right? So L to the power of minus half, right? But here I had to take it as it is. So 1 only I had to represent here, not minus 1. Yeah, to the half. And one more value also you're supposed to put it here, right? Half into, just a second, let me put the square bracket. In that one I had write L cube. So an equation is wrong, so let me correct it for you all. Yeah, this one, right? So I think now it is clear. So you can see it here, right? So this is the equation, right? So t value is L to the power of 1 L cube L to the power of minus f into the power of half it is. So this will be the value for t, right? And we'll multiply the same thing into L cube, right? Then we will be getting this equations here. So just verify whether you're getting the same answer or not. If you're not getting the same answer, we'll try to see it here, right? So this is the values for the rigid body dynamics itself here. Now let us go for the next heading, that is scaling in electrostatic forces here. So we'll try to take how the electrostatic forces can be applied when you scale down to the miniaturization here. So that one we'll try to discuss now here. So when you go for this electrostatic forces here, we will be taking two parallel plates here. So you can see it in this figure, you're having two parallel plates. So we'll take these two parallel plates here, right? And for these two parallel plates, we'll try to represent the mathematical expression here. So where these two parallel plates will represent in the form of parallel plate capacitor here. So in the form of parallel plate capacitors, these two will be represented here. So there will be some gap between these two. That gap is given by D, right? And there will be the electric potential energy will be created between these two plates by applying the voltage here. So these are electrically charged parallel plates here, where you can see, and you will be having the distance gap between these two parallel plates equal to small d value here. And if you take the parallel plates here, the width of the parallel plate is W and the length of the parallel plate is taken as L itself here. So in this way we will be taking here the two parallel plates here, and this is the configuration of this parallel plate here. And what is the electric potential that is being induced between these two parallel plates here? So that electric potential is given by U here. So the electric potential energy, right? Electric potential energy that is induced between these two parallel plates is given by minus of half into C into V square here. So where we can also represent that one as the capacitance value in the form of epsilon naught into epsilon r. So where these two are nothing but the permittivities, right? And W into L, the value of the capacitance is taken by W into L here, right? C value is nothing but what? C is nothing but epsilon naught into epsilon r into W into L divided by D. So that value is been substituted here into V square here. So where what is V? V is nothing but the applied voltage. So what here usually we call this one as the V is often called as what? Electric breakdown voltage of this capacitor itself. So this is the electric potential, right? Electric potential energy that is induced between these two parallel plates is given by minus into epsilon naught into epsilon r WL V square divided by 2D itself here. Now, so after we had analyzed the electric breakdown, electrically charged parallel plates here. So what would be the voltage? We had already calculated here. So the breakdown voltage, right? The breakdown voltage V here, right? If you see the V here, so it will be varying, right? It will be varying between these two parallel plates, right? If I see between these two parallel plates, this breakdown voltage V, what we calculate here, this breakdown voltage V will be varying, right? It will be varying as this gap will be varying here. So if this gap varies, then automatically this induced electric breakdown voltage will also be changing itself here. So that change, right, that change between these two parallel plates as the gap changes, how the breakdown voltage will change, that will be analyzed in Bastian effect here. So the Bastian effect will see, right, this Bastian effect will give you how this gap, right, when you change the distance between the two parallel plates, that is this gap D here, how this breakdown voltage will change here. So if you see it here, right, so if I see the gap is around 5 micrometer, then what happens, the breakdown voltage will be around at this point. Now if I increase the gap, right, if I reduce the gap here, then what happens, the breakdown will be still more reduced here. So you can see it here, right, this breakdown voltage V, it will drop drastically. So this breakdown voltage will drop drastically with an increase of the gap, right, with the increase of the gap D to be less than 5 micrometer. So if this gap is very much less than 5 micrometer, then automatically this voltage will be dropped here. However, if you slowly increase the gap, right, if I slowly increase the gap greater than 5 micrometer, then automatically you can see the widen, right, you can see this widen here. So how much should be there, appropriately how much should be here? So the variation will be varying at around 10 micrometer. You can see it in this figure, how the variation of this voltage will be reversing at this point here. It will be reversing at this point here. So if you see it here, the breakdown voltage will continuously increase at this point, right? At this point you can see it is continuously increasing, right? It is continuously increasing. Further, if you go on, increase the gap here. So if you further increase it, then automatically it will go on increase here. But at point of, right, at the point of D equal to 10 micrometer, the variation will be reversed. So that one you can consider here. So here at starting, what happens at initially, if you go on increase this gap, then the breakdown voltage will reduce. But at one point at 10 micrometer here, what happens, slowly it will be widening, right? Slowly it will be widening. If you increase more here, what happens, then automatically there will be a linear increase in the voltage itself. You can see this one in this figure. Understood all of them, the Paston effect? Shall we go further? Yes, are you all online? What about others? Why they are not attending the classes? See that all of them attend the classes, because from the recording only I'll be taking the attendance and put for the attendance sheet here. See that when you'll come to the next classes, all of them attend it. Understood all of them? Shall we go further? Yes? I want the responses. Shall we go further?
Yes, ma'am.
Now, let us go for how to calculate that one, right? So we have calculated this one, and when you apply this Paston effect, what happens? We can see that one, right? So we can assert that whatever the applied voltage it is there, it will be depending upon what? It will be depending upon the gap between the two parallel plates here. So we can take the applied voltage is directly proportional to the gap, or if you take in scaling, right, the VE is directly proportional to the L to the power of 1 here. So in scaling, we have to represent it down here, because we are scaling down this effect itself here. So what we'll do, we'll take the working range. So what would be the working range here? We have to take the working range that D is directly proportional, D should be at least greater than 10 micrometer, right? You can see in this, sorry. Yeah, you can see when if you take D is greater than 10 micrometer, then automatically there will be a linear, right? There will be linearity in increase in the as you go on increase the gap, then there will be linearity increase in the breakdown voltage here. So we'll take that one into effect here, right? So what we'll take, we'll take the working range. We'll take that working range where D is greater than 10 micrometer, and the scaling of that value, right? we'll take the scaling value, right? With the scaling value V to be directly proportional to L to the power of 1 and D to be greater than 10 micrometer, and the scaling values for epsilon naught and epsilon R will take it to be L to the power of 0 here. So these constants will be taken as 1 here. Now for that one, let us represent the electrostatic potential energy here. Now what is the electrostatic potential energy equation here? We know that it is equal to what? Minus epsilon naught into epsilon R into W into L into V square by 2D. So since we have taken these values of L to the power of 0, right? So you can see epsilon naught, epsilon R, right? And W we have taken as L1. L also we have taken as L1 itself here. Next, V square is represented by L to the power of 1 into square divided by D. So that one is also taken as L to the power of 1 itself. And the constants we have just left it out here, right? So what we'll get here? We'll be getting L cube. So you can see it in this figure, it is L cube here. So the above equation, what does it represent here is that a factor of 10, if we decrease in the linear dimension, then how much it will decrease here? The potential energy will reduce by 1000 here. So if you reduce this, all these factors W, L and D simultaneously in linear dimensions, if you reduce it to a factor of 10, then automatically the potential energy will reduce by a factor of 10 to the power of 3. That is the scaling value. That is the scaling value you can calculate for electrostatic energy. Provided what we had to do, we had to take the gap between the two parallel plates to be greater than 10 micrometer only. So that gap should be maintained here, or else you will not be able to get these results here. Now, if you take the scaling laws, right? If you take the scaling laws here, the electrostatic forces that is being produced in 3 dimensions, it will be produced in 3 dimensions here. So that one is given. We'll try to take that one, right? We'll be having 3 dimensions. One is D, right? One is D. Second one is W, and third one is the L itself here. So we'll take all the 3 directions for the analysis. So I think I have not given. Okay, so here I'll just represent for this one here. So if I take in the W direction, right? If I take in the W direction, it is FW, right? If I take in L direction, then it is FL. If I take in D direction, then that will be FD. So I think now you are aware of it, right? So you're having what? You're having in 3 directions. So what are the 3 directions is? One is in the direction of D, second one is in the direction of W, and another one is in the direction of L here. So these are the electrostatic forces. So you'll be getting almost all the equations same, except we'll be having this term changed here. So if I take in the D direction, we'll be having both the terms W and L. If I take in W direction, we have to take only L. If I take it in the L direction, we have to take the W itself, and other factors will remain the same here. So you can see all these 3 components, all the 3 force components, that is FD, FW and FL in the 3 directions, all are what? All are directly proportional to L square here. So which means that the electrostatic forces of order of 2 is in the scaling as in table 1 here. So let me show you the table 1. This one is the table 1 here. So if you see it here, this is the table 1 here, right? So this is the in the form. If you take in the order of 2, it is L square. So that equation only will be constrained. So since it is in the order of 2, right? Electrostatic forces are in the order of 2. So the scaling factor will be how much? It will be just L square. So what does it indicate, right? So if you reduce the size of the parallel plates, if I reduce it to 10 times, then automatically the electrostatic forces will reduce to 100 times here. So that is the proportionality, right? That is the proportionality we'll be obtaining whenever you scale down to the size itself here, right? So this is about the electrostatic forces. Understood all of them? Shall you go for electromagnetic statistics? Right, we will try to discuss now the electromagnetic forces, right? I will be having 2 only component here. One is electromagnetic force, next one is in electricity, and the last one will be fluid mechanics. 6.7 I will be having the fluid mechanics and scaling in heat transfer. So I think in the next 1 or 2 classes we'll be able to complete this one. I hope you understood, right? Shall we go for the electromagnetic forces here? How we can scale down? Yes, I want responses.
Yes, ma'am.
Okay. So this is about the electrostatic forces here, how we can scale down itself. Now we'll go for the electromagnetic forces here. How do we scale down in electromagnetic forces? So scaling down in electromagnetic forces, when you apply here, we have to take the classical electromagnetic theory for that one in order to understand in electromagnetic forces here. Just a second. It is scaling, right? Scaling in electromagnetic forces. So you can see it here, right? We had to understand a few theory about electromagnetic forces here. So where F, right? F will be what? How the F will be induced here. So it can be induced in a conductor or a conducting loop in magnetic field B by passing the current through the conductor itself here. So whenever you want to analyze this electromagnetic forces here, the electromagnetic force is nothing but which is the actuation what we obtained in the classical means, right? So that classical means should be considered and we'll try to analyze that one. So when you bring back this electromagnetic forces here from the most machines in micro scales to the micro levels itself here, then we have to take, right, we have to consider how it is brought down and where do we use this one. Electromagnetic forces will be using current will be using in cars, right? So in miniaturized cars we can use this method itself here. But how do you, let us take for example the classical, right? So if you take the classical electromagnetic force, how it is induced, so the F can be induced for a conductor or a conducting loop itself, where it will be in the magnetic field B by passing the current through the conductor itself. For that magnetic field, what will be the electromagnetic force, we'll try to be able to calculate here. So what we'll do is we'll take one mathematical formation for that one here. So where we'll be representing the B, right? B will be representing here. So this B is nothing but we'll take that one as the what magnitude of the magnetic field. So where B is nothing but what, it is nothing but the magnitude of the magnetic field, so which will be in the form of what unit of Webers per square meter, and automatically I is not represented as what the current in amperes. So the electric current which is flowing through the conductor, it will be in the form of the flow of electrons, right? Flow of electrons per unit time and area, right? And how we represent that one? So the current is given by what? Q by T. So where Q is nothing but the charge per unit area, right? Charge per unit area of that conductor, and T is nothing but the time. So this is the expression for the current itself here, right? So now let us calculate the electromagnetic force here. So the EMF, electromagnetic force is nothing but EMF itself here. So the EMF is nothing but it will drive the electrons through that conductor. So when you're allowing the conductor for allowing the current to pass through the conductor, then EMF is induced. So that EMF, the energy for that for the energy required to drive these charges, that is the electrons through the conductor, is represented by U here. So where U is nothing but integral of D into U itself, so which is taken as E into dq here, right? So integral of E into dq will give you the equation for the force, right? That is the force that is been induced when the current is been carrying here. So for the current carrying conductor in magnetic field here, we'll be having the magnetic flux, which is nothing, which is given by the equation by Faraday's law itself here. So where you can express this induced EMF in the conductor in the form of coil with N turns. So the induced EMF, right, is represented by N into d phi by flux, the d phi by dt itself here. So what will we will substitute this one in equation 12. So what I'll get, U is equal to integral of d phi of t by dt into I dt, right? So you can take further into dt. So one more this dt will be cancelling off. So what I'll get, integral of I into d phi. So which can be represented as 1 by L, right? D phi of t into uh, d phi of t itself here. So where the current I, right? The current I is represented by equation what? I is nothing but Q by T. So we'll take this one q by t here and substitute, right? So this q by t will be taking itself here, right, and substituting, right? So phi of t by L will substitute here. So here this L is nothing but what? L is given by phi of t by phi of L I by L. So the inductance will try to replace the current with the inductance value. So we can represent that one here, right? So this is the equation for the EMF. This is the equation for EMF which is given in equation 13. So here we are taking for the number of turns, right? The number of turns is taken for 1. For n equal to 1, we have derived this equation itself here. So this represents the value for EMF. This is the equation for EMF here. So what we'll do? We'll try to take this equation 13, right? U is equal to 1 by L phi of t into d phi of t. And what we'll do, we'll try to integrate that one. So once you integrate, what I'll get? I'll get half outside, half into phi square by L, right? Phi square by L, or we can also get it as U equal to what? 1 by 2 into L into I square. So we will substitute 5 by half, we take represent in the form of current equations here. So that one we can represent here, and we'll be able to get U value equal to half into L I square here. So this is the induced electromagnetic forces here. But here what happens? The force induced, right? The force induced will change, the induced EMF will change whenever there is a change in the relative position of the conductor in the magnetic field. So if the position of the conductor changes, then automatically this EMF will also change. So then this equation will not hold good. So then what we had to do, we had to take the expression for these forces, right? We had to take the expression for these forces whenever the relative position of the conductor in the magnetic field changes. So then what we'll get? The F value, right? The F value will be taken as du by dx, where phi is substituted as constant, or when I is remaining constant. So either of this one we had to consider, right? So if you consider the case with constant current, then what happens? This equation 15b, this equation 15b, the induced electromagnetic force will be represented as this one. So half into I square into dou L by dou x, provided we'll be having the constant current. So suppose if I take this second equation and assume that we are having constant current flow, then this will be your induced EF itself here, right? So this one we will take it here, right? We'll not take the EMF as constant, but we'll take the current as constant itself here. So for this one, where the constant current flow has been assumed, the induced electromagnetic force is given by half into I square into dou L by dou x. So take this equation here. So when you take the 16th equation here, the current I, right? So the current I, which will depend upon what? It will depend upon the area of the conductor here. So where I is directly proportional to L square here. And dou L by dou x, it is dimensionless value. So we'll not take that one. So what would be our scaling down of electromagnetic force here? So F is directly proportional to I here. I is taken as L square, right? So L square is been considered into L square itself. So since L is given, so that one is represented by the L square itself here. But this one will be taken, dou L by dou x will be taken as a dimensional value. So hence the scaling down of electromagnetic forces is given by this one, right? L to the power of 4. So these parameters are being considered here. So L by inductance, the inductance into L square. So the inductance will be taken in the form of L square here into L square, which will be equal to L to the power of 4. So this will be the value for the electromagnetic force here. So what happens? What is the inference for this one here? So if I reduce, right? If I reduce the size of the size of the with respect to electromagnetic force, if I scale down to 10 times for the reduction of the size, then it will lead to what? It will lead to L to the power of 4 times, 10,000 times in the reduction in the electromagnetic force. So this scaling should be considered here. So there is a contrast here. If you take the contrast between this electromagnetic and electrostatic forces here, if you see it here, in electrostatic force it is L square, means only 100 times it reduction takes place, but here it is L to the power of 4 times here. So the electromagnetic forces are 100 times less favorable when compared to electrostatic forces here. So why if this electrostatic force, right? Electrostatic force here, it will explain what? It will explain that all these micrometers micromotors, actuators that have been built using electrostatic forces rather than the electromagnetic forces here. So we'll try to choose electrostatic over the electromagnetic forces here. And also we don't have, right, we don't have much spaces for micro devices here that will induce sufficient magnetic field actuation power here. So the if you take in order to accommodate this inductance, right, so the inductance plays a vital role here in order to accommodate this coil inductance. So then that will be it will take much space for that one, so that will be it doesn't give you smaller sizes here, so that is the drawback here. So that's what, right? So we since for that sake we'll be going for electrostatic actuation rather than electromagnetic uh, size itself here, right? I hope you understood all of them. So this is about scaling in electromagnetic forces here. So I hope you have understood, right?